All right, so Pre-Calculus 30, Section 1.2, this is Part 2. We talked about reflections in the last lesson, and today we're going to focus on the stretches of functions. And I often refer to the original function as that's one of the things I call it, an original function. But I kind of slipped up a couple years ago and accidentally called it the mother function. And actually, the students really thought that was great. They thought that was a great name for that. Because, if we move a function, it's almost like it gives birth to another one, right? If we take a function and we create another one from it, it's almost like it is parenting this or giving birth to another function. So, I guess we may as well just get this out of the way that I might call the original function the mother function, okay? Now, you have to be real careful about how we share this information with those not in this class. For example, I don't want to hear you guys out in the street calling to me if you see me, "Hey, mother function!" Because it might not sound quite right. People might say, "What did he just call his teacher?" Okay, so, and you can see on the tiles here, right, I have, there's definitely mother function is mentioned on one of those tiles up there, okay, when we first coined that phrase. So, let's just get that out of the way. You see it up there? Okay. Now, so if we go back, look at this here. Remember this from last lesson? Okay. The graph that's in blue is the what? It's the mother function. Look at that mother function right there. Okay. Now, listen. It might be sort of freeing for you just to say it out loud with me. So why don't we just say it? We'll say mother function on the count of 3. Okay. I know this is a bit awkward, but let's just get it out. Let's just get it over with. All right. So ready on the count of 3. Ready? 1, 2, 3. Mother function. Okay, that was pretty lame. But you guys are so cerebral. You're so intelligent that's not funny to you, right? No one's smirking. Okay, good. So now that we got that out of the way, this is the mother function, right? And what we're going to do is we're going to now give birth to another function, and we are going to now talk about stretches. So what are they, first of all? The stretch is a transformation in which the distance of each x-coordinate or y-coordinate from the line of reflection is multiplied by some scale factor. Okay? So, this is a lot of technical gobbledygook right here. Okay? What this means is that only one of the coordinates of each point is altered, and it's actually multiplied by a scale factor, either a fraction or a whole number or whatever, an integer. So, basically, a stretches is when f of x, the original what? Mother function, changes shape. Changes shape. Okay, that's huge. With reflections, the function, no matter what it was, if it's parabola or something strange, it just flipped. It was the same shape. It just changed orientation, right? Upside down, left, right, whatever it was. So now, stretches, we're talking about how do we manipulate a function in order to change its shape. And that's what we're going to do. So this shape right here, this function right here, looks like a W, right? Looks like a W. If we are going to use a scale factor, and this little note down here, what does this say? Scale factors between 0 and 1, so that's like a fraction, brings the points closer to the line of reflection. The scale factors that are multiplied greater than 1, move them further away. Now, I don't put a whole lot of stock in this because it's kind of confusing until you go through a few examples, and I want to show you kind of how that works, okay? So the first type of stretch that I should talk about with you here is this type of stretch, okay? So when we have a new function here, and we'll do it in black, where we have some number, all right, outside of whatever the function is. So it's like a times f of x. Okay? A times f of x. Okay, so let's see. So now, remember we talked about a negative out here for reflection and a negative inside for reflection? If a is negative 1, we have a reflection. We don't have a stretch, really. We just have a flip. But what if a is not negative 1? If it's a positive 1.5, or if it's negative 0.7. That's what we're going to talk about. It actually, the graph changes shape. And really, if you think about this, okay, and you can look on page 27 too if you want. We're going to be dealing with the example, and actually this example starts on page 21, but 27 is the summary page. So what we're going to do is we're going to look at what is the graph of, and I'll show this in red maybe, y equals 2f of x. Okay? So if you think about this, right, f of x in the original function is equal to y. So if we are putting a scalar, or a number that we're multiplying f of x by, it's like we're multiplying that number by y. So that's when we alter the y values. So if you have a 2 in front of f of x like this, we are changing the y values. So it's basically y values times 2. That's what this really means. It's the y values for all of the points on this graph times 2. That's what that literally means. So what does that look like? Well, let's take any point. Let's take this, start with the 2 here, okay? So this point is 0, 2. So what would this point be equal to if I multiplied just the y value by 2? It would be 0, 4. Very good. Now, if there was a line of reflection, it would be the x-axis, right? If we're talking about that 1 versus negative 1, it's the x-axis, flipped that way. So notice how this point, this number is greater than 2. So what this says, greater than 2, scale factors greater than 1, that's what 2 is. It's moving away from the line of reflection. I wouldn't, like I said, let's just talk about this more later. But that is consistent with what you see over here. All right, now what about this one? This is the point 2, 0 in the blue graph. So if I multiply the y coordinate by 2, what do I get? Oh, I get the same. So that is, what kind of point is that again? Invariant. Does everyone see that if I am right at the line of reflection and I go double the distance that I already am from the line of reflection, 2 times 0 is still 0? See that? All right. So the same would be over here, right? The new point is over there. Now what about this one over here? This blue point here, that is the point negative 6 and 4. Right? So what does this point become? Negative 6, 8. Absolutely. Negative 6, 8. So I am doubling the y values. Okay? So if I follow this over here as well, and I take any other point, I can take any other point like this one, right? This is a y value of 2, so let's make that a y value of 4, and so on. Here's a y value of 1, let's make that a y value of 2. And you see how I'm kind of piecing this together here? Y value of 1 becomes a y value of 2. You see that? Well, here's 2 becomes 4. Here's 3 becomes 6, and so on. And so if you piece all that together, you get a new graph that, yes, is still sort of a W, a recognizable W, but it's definitely changed shape. And you could say that this W has definitely been stretched upwards, right? Okay? So it's stretched taller. All right. So let's pop over to this right here. Now this is not a W, but this is, let's take that off. And actually, I'll leave that y equals x squared. So look at what I've got set up here on Desmos, right? I've got a value here, A1, that is going to be like our A in our last example. So if I've got the y equals x squared, and A is 1, that is the same as y equals x squared. So actually both graphs are right on top of each other. You see that? Can't really see that. But I'm going to move this now to 2. So watch what happens to this black graph when I move it to 2. Now you might look at that and you say, Mr. Maxwell, I saw that move inward. I saw it get squished up and not moved up. You know, parabolas are kind of tricky that way. It's kind of hard for them for you to see that. But what happened was each point, so here's 1, 1, right? Look at, now it's 1, 2. All right? So this one was, let's say this was 0.5 right about here. Now it's 1. See? If we don't use a parabola, let's go back to, oh, which one's that one? Oh yeah, this one right here. Let's light this thing up here. Oh, come on. Yellow. Okay, see it down there, right? Remember this one? Let's zoom in there just a bit. Okay, so now it's at negative 1. If we set this equal to 1, you know what this looks like, right? Okay, and I'm going to have to change change this to, let's go with like 5, and we can go, I don't know, just 0 there. Okay, so there's 1. Now, if I increase A, that should do what to this graph? It should stretch it vertically, right? So a stretch vertically. If I go greater than 1, so let's see. Oh, now this one is pretty strange because this part here is going down, but these other parts seem to be going up. So remember how that definition there where it said it's going to get further from the line of reflection? So what would be the line of reflection? So that's what's happening here. It is being stretched, see? Stretch, stretch, stretch. Now if I went back to 1, and we took a look at this graph at 1, 1. Now what if I went to, closer to 0? If I went closer to 0, guess what? It's getting now squashed. Okay, so that still is a vertical stretch, but it's by a factor of, less than 1. And I like to call that like a compression, When you compress things, you squish it up. So this is like a vertical compression when A is between 0 and 1. So again, here's 1, okay? Here's 2, here's 5, here's 7, all right? And here is 0.5, 0.8. Oh my goodness, what did I just do? Oh. Okay. Can I do 0.8? Yeah, 0.8. 0.9. All right, that's getting closer to 1. One more. 0.1. Okay, really squished up, see? It's getting compressed towards, okay, that's enough of that. Let's go back to our notes. They're gone. No, they're there. Okay, good. Okay, so it would make sense, hopefully, that if I change this to, really quickly, if I change this to, say black, to 1/2. Does everyone see how these y values on the original mother function would go down by 1/2? This one, 1/2 of its value. This one, 1/2 of its value. See? This one, 1/2 of its value. This one, 1/2 of its value. This one stays at 0, because 1/2 of 0 is 0. 1/2 of its value, 1/2 of its value, 1/2 of its value. See that? And so what we have is we have this graph that is now compressed vertically. See that? And I think that's what the next graph is, and I don't know if I've copied that out, but there's in the blue, that's the original function. The red graph has a scalar a value of 2, so it's stretched vertically by a factor of 2, and over here we have a factor of 1/2, so it's been compressed. It's actually been compressed by a factor of 2, or stretched by a factor of 1/2. Make sense? So we're pressing it down, 1/2, or we're, whatever. There's just the wording there. But. Okay? All right. Awesome. Okay, let's go back to the textbook here. And of course, here we go, nice and neat. See, there's the red graph. It's been stretched by a factor of 2. And here they set up this table where every y value has been doubled. And that's what we did. 0 times 2 is 0, 2 to 4, 0 to 0, 4 to 8. Okay? And here's the 1/2 graph. See? All the y values have been multiplied by 1/2 to come down times 1/2. And it's compressed. Questions? Any questions for that? Yes? Okay, that's a good question. Is the x-axis always a line of reflection? If there is a translation involved, for example, if this original graph, if it has been translated upwards at all, then the actual line of reflection would move. Okay? So, yes and no. Oh, I tell you what, let's go back here and let's explore that a little bit. Okay? So, let's say I have this graph, right? And let's go kind of like 1-ish. Okay? Now let's say I alter this and I go +1. Do you see how that's moved up there? Okay? So what we're going to check out is if A moves, And see, if A is only multiplied by this part, you see A only is multiplied by this part. So A affects the main kind of body of the graph, but this 1 now translates it from 0 up to 1 here, right? So let's see, if we move this, look what happens. See, it still kind of stretches according to what would be this line of reflection, which would be right here. Now, if this A value was applied over the entire thing, including this plus 1, what would that look like? So let's do this. Okay, now, and again, let's just see. So what's going to happen? Whoa, look at that. Now, we aren't going to deal too much with this type of graph, but you see how it does, see, it's still the x-axis here because there's no k value there. Okay, so if there's a k value involved, really that k value is the line of reflection. Okay, let's just say that. If there's no k value involved, like if it's 0, then y equals 0 is the line of reflection. And so yeah, this is actually kind of cool how this sort of reflects. But let's zoom out a bit. So yeah, so it stretches and reflects, and it kind of moves away as well from that line of reflection, which is super cool. We aren't going to deal with too many functions like this. But yeah, that is super cool. Okay, so let's go back here, and we'll just make that like it was. Okay, so, but that's a great question. Okay, so that k value is going to be your line of reflection, really, if it's in this form. All right, moving along. Now we have to talk about this. What this would be this b value here. Okay, because if we have a vertical component to a stretch, guess what other component we also have to a stretch? Horizontal, right? So anything that we did inside the brackets with the x before represent a horizontal shift, right? If it was x minus 2, that means the graph shifted to the right 2 units. So if we now have a scalar inside for x, that's going to represent a horizontal stretch. Okay? So let's explore that one a little bit. And we'll just look at the textbook here. You have that in your books. No sense to, we can, and we might recopy this, but let's just take a look at it, okay? So what happens if we have a 2 inside with the x, all right? The 2 inside with the x. Now, I don't really like the table of values quite so much. It's a little complicated, but you see, these are the original points, aren't they, on the original blue graph, okay? And so basically what they're saying is that the y value has to stay the same. It's the x value that's going to change. So in order to keep, okay, let me just zoom in here. In order to keep, there we go. In order to keep y equals 4, and I replaced x with 2x, what x value would I now be multiplying by to give the same input value that I originally had? Or 2x now equals the original x. So what happens is the new x value is half. Okay, let me say that one more time, because I think it's on the confusing side, okay? So if we have an original point of -2, 0, and it's now in the form of the new function is f of 2 times some number to yield the same y value, well, I have to take this x value, which is 1x, and now I have to cut the x value in half because I'm multiplying it by 2. What this means is if we look at the graph here, okay, that a factor of 2 would mean that each x value is basically cut in half. Okay, so it works kind of opposite. If we have a number greater than 1 for a b value, the graph is squished up. It does not stretch out, it gets squished up. Okay, so a factor of 2 would mean 1 over 2 for each x value. Okay, and I think that that's what they talk about here in green. So it says the horizontal distances of the transform graph have been changed by a factor of 1 over b. That's entirely true right there. And that's when b is greater than 1. Okay? So we're not talking about positive, negative, any reflections. We're just talking about just actual number, absolute value. So if we have a 2, then you take the x values of the original function, and you multiply them by 1 over 2. If we have a b value of 5, so if it's y equals f of 5x, then each x value is multiplied by 1 over 5. Okay? So the big thing you want to remember is if b is greater than 1, it gets squished horizontally or compressed horizontally. That means that each x value, so in this case for this point it's 4, the x value will be cut in half. Same y value, but it's cut in half. See that? There's the new x value. This one right here is 3. So it gets cut in half to 1.5, and that's true. That's what it is. Okay? Everything gets squished up. Okay, so just to get some practice here, if this blue one is our mother function, then what we're going to do is we're going to apply this stretch here. Now, if b is 2, that means we are going to be compressed, or it's going to be stretched by a factor of 1 over 2. And what is going to be changed? The x values or the y values? The x values, because this number is in with the x. So mapping notation here, it's going to be basically 1 over b, 1/2 x, and the same y value. That's the mapping notation. Each x value is going to be multiplied by 1 over 2. So, 2, x value of 2 here, multiplied by half, that turns into a 1. This point up here is an x value of 6. So it's going to turn into an x value of what? 3. Half of 6. Any other point will work here as well. So look at this. X equals 4 goes to x equals 2. X equals 3 goes to x equals 1.5, and so on. Positive, negative, everything. Right? Okay, so the negative 2 comes to negative 1. The negative 6 goes to negative 3, and so on. Okay? So if we connect these dots here, again, I'll do my best with this straight line business here. If we connect these dots, then we have this sort of thing happening, right? The whole thing is compressed towards the line of reflection. So each x value is multiplied by 1 over 2. So that's y equals f of 2x. Questions on that? So in red then, and I'll do this just a little bit quicker, if we have 1/2 x, remember the mapping notation is 1 over b, so that's like 2x, and the same y, that's the mapping notation. So if we have a half, it's 1 over a half, which is 2. So, let's see, for 2 becomes 4. 6 becomes, well, I don't have room for it, but it's going to become 12, right? 3 becomes 6. And I have 4 here becomes 8, so I can do those ones. Okay? So 0, obviously, x equals 0 times 2 is still 0, so that's why these are invariant points here in the middle. Okay, but 1 becomes 2, and so on. So we'll kind of complete some of these here. 2 to 4, 3 to 6, and so on. Okay, so here is your graph in red with the b value of 1/2. It gets stretched horizontally outwards. So again, if we go back to our graph here, we're going to take a look at this graph. Y equals x to the power of 6 plus x cubed, and that's what this looks like, right? And so what happens if I actually change, this is the b value inside, so right? So each x value, if it gets multiplied by 2, so I'm going to move this slider over here to 2, then what happens? Well, I've got the original graph, and I've got this graph here with g equals 1. So if we go to 2, look at what's happening to it. Going all the way up to 2. You see how it's been compressed, right? By a factor of 1/2. If I go more then it's going to get squished up even more, right? What happens if I go from 1, which is right here, the same as the original graph, and I go down, okay? If that number gets lower, so there's 0.5, look at each x value has been doubled. Each x value has been doubled. Each x value has been doubled. See that? 1 over 2. And so on. The closer you get to 0, the closer that graph gets to y equals 0. Right? Alright, so there you go. Let's play that. Whoa, slow down. Okay? So there it's getting larger. Right? Going up to 5, it's getting squished, 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 squished. And once it hits 5, it comes back down. See that? Yes, that's right. It's like some sort of like, yeah, some sort of like Indian dance or something, isn't it? Isn't it? I don't know. Maybe you see that in the cave walls somewhere. I think we see this sort of dance, sort of movement. Anyways, all right. So you get that? Questions? Thoughts? Comments? Okay. Awesome. As we conclude here, here's the summary page again, which is really good. There's the reflections up top. And if we look now, focus on the bottom here, we have the A value is a vertical stretch. Right? If A is greater than 1, then it stretches away from the line of reflection. If it's less than 1, it gets compressed down. And of course, if it's negative, guys, if it's negative, it's going to be flipped. If it's negative 1. If it's negative 2, what's going to happen to this mother function right here, the blue graph, if A is negative 2? What's going to happen? It's going to be what? It's going to be flipped, yes, because it's negative. What else? Is it going to be stretched as well? Yeah, it's going to be flipped and stretched, okay? So this is what happened. They're just talking about values greater than 0, okay? Just to introduce that. But I think you guys are ready for the fact that, hey, if A is negative, it's flipped. If it's greater than 1, it's flipped and stretched vertically. If it's negative and between 0 and 1, it's going to be flipped and compressed. Right? Okay, maybe you're not there yet, I don't know. But this is all you need to know here. What A does, what B does. Okay? So B is the horizontal, A is the vertical. And of course there's the mapping notation as well. I will go back to, let's see, back to Desmos here. And if I, okay, let's make this 1. Okay, so actually let's get rid of that. So this graph, no, let's put it back. This graph right here, up here, if I make this negative, it flips, right? There's negative 1. And of course if I keep going, it's flipped and stretched, see? So there's negative 5.5. Flipped because it's negative, and stretched because it's greater than 1, the absolute value, right? Yes? Good? All right, so if we go back to the notes here, the homework that I gave you last day, you'll be able to complete all of that now, so please go ahead and do that. Wow. 1.2, page 28, you can complete all of these. That would be awesome.